Hey, Honors Physics. This is a kind of a follow-up to page 20, and I do want to show you a model of what happens to the concept of work or non-conservative work due to friction when we have something that's a little bit different. We have the friction on an inclined plane. Now, this year has been very challenging for some, and one thing that has been challenging is that while we have mastered many physics principles, we never did really fully appreciate all the nuances of forces on hills. Many of you did, but some people still have some challenge. So this is to reinforce what we did then. Okay, so but we're still in the energy unit. So from that principle, what we really need to do is we need to start off with a thought process, just like any other problem, of what kind of energy. Let's take inventory of the kinetic energy, the potential energy due to gravity, or spring potential energy. And I can see two ideas, right? We've got a velocity right here, and we've got a height right here. So I'm thinking off the bat that there's only two kinds of energy: potential energy due to gravity and some kinetic energy. Both of these are true at position A, okay? So here comes the snowboarder or the skateboarder, and he's about to whiz down this hill. But this hill is not just what we've been seeing so far. This hill has some coefficient of friction between the board and the surface. So as soon as you see a friction force that's implied, you know that there's going to be some work that is not going to conserve the mechanical energy. So we call it non-conservative work. But at the very bottom of the hill, right, there's no height, there's no spring, but there has to be, or there is likely to be, some kinetic energy left over. So there's a pretty good setup for a typical conservation of energy problem. And there's work being done down a hill. So let's dig in as far as we can get. So we've got mass times gravity times height. We've got 1/2 mv squared. And of course, the formula for work, regardless of whether it's on a hill or not, is there is a friction force, but it is multiplied by the distance along the hill, right? We're going to have to find that distance. And we're, of course, going to multiply it by cosine of 180. Sorry, I'm getting ahead of myself. Let's go back a step. We don't know that it's 180 yet. It probably will be, but we know it's cosine of theta. And at the very end, there's some kinetic energy. So I think it is worth our while to not immediately jump into plugging in the known, like the mass, the gravity, and the height, but let's focus on what would be the free body diagram on the hill. So I'm going to challenge us to draw it a separate time. We've got a hill that has a slope of 40 degrees or a pitch of 40 degrees. And what we know is that there's an object sliding down this hill. And while you're on the hill, right, let's talk about all the forces that are there. I hope you remember that we, of course, always perpetually have a force of gravity. It's toward the center of the Earth. And we have a force of gravity that's perpendicular to the hill. We call it FGY. And that leaves us with FGX. And remember, the key thing to draw is FGX needs to be parallel to the hill. What else do we know? Well, the hill has a normal force on it. And the normal force would be equal and opposite to the FGY. And that's going to be really important in a little bit because the friction force is related to the normal force. So where's the friction? We haven't even drawn in the friction yet. Well, the friction is this way. It's, of course, kinetic friction. And that is going to be the key force that we need to use. Let's see, any other small nuances? Let's remember how to find each of these forces. Fg is, of course, oops, let's fix that. Fg is, of course, m times g. Fgx is opposite the 40-degree angle of the hill. So this is going to be mg sine theta. Fgy is mg cosine theta. And while we're at it, we'll remind ourselves of our formula for Fx, or Fk, excuse me. And the formula for kinetic friction is, of course, mu times normal. So that's going to get us on our way. Hopefully reviewing those forces was something you can do. There is one more thing we're going to have to find out, and that's how long is the hill, but we'll save that. So let's continue with our formula development, because I think that review of the free body diagram is going to help us. So how do I find the kinetic friction? Well, the formula is mu times normal. But I'm going to take a jump here, and I'm going to, hopefully you're going to follow and say, well, I don't actually want to know the normal force, but the normal force we believe is equal and opposite to FGY. So if I want to represent the friction force, which is mu times normal, I could rewrite it as mu times mg cosine theta. Now, what theta are we talking about? We're talking about the angle of the hill. So all of that replaces kinetic friction. We still need to know the distance. Now, here's another question. Is it the same theta? Because this equation is getting a little bit complicated because there's another theta in here. But remember, that's the angle between the friction vector and the displacement. Well, the friction is, of course, up the hill, but the displacement is down the hill. So that is going to be an example where we're going to use cosine of 180 degrees, not this angle of the hill, but the angle between the friction force and the displacement while you're skidding down the hill, sliding down the hill. Okay, so it takes arguably more time to set it up than to actually solve it. Notice the unknown is v over here, so we're still a little stuck. We don't know the distance or the length of this hill, but here's how you do it. You know that the height of this hill is 15 meters. You know that the angle is 40. So I could use a little bit of basic triangle trigonometry, not vectors really, and just simply say, if my opposite side is 15 and I want to know the length of the hypotenuse, what trig function has opposite and hypotenuse in it? And it's sine of 40 degrees is equal to 15 over the hypotenuse. So my hypotenuse is going to be 15 divided by sine 40. Or my hypotenuse, or the length of my hill, is 23.3 meters. So from here to here. And I did that by seeing a right triangle. I made a right triangle that would help me out. Okay, so I think we're ready to plug in. And kind of right off the bat, before I decide to do that, I actually notice that there's a mass in every term. So we're going to cancel that out. 9.8 times the height of 15 meters, plus 1/2 times the velocity of 5 squared, or 25 meters squared per second squared, plus mu, which is 0.4 times 9.8, times cosine of 40 degrees, the angle of the hill, and times a distance. We just calculated the distance, 23.3 times a -1. Boy, are the details really challenging to track, but you can rewatch that. I went very meticulously through, plugged in each one, cosine of 40 degrees, distance 23.3 meters, the cosine of the angle between the force and the displacement, and finally on the right-hand side, 1/2 of v squared. So this is really a really advanced application of conservation of energy with work involved. And the details are what will get you. They're really challenging. So 9.8 times 15 is 147. Half of 25 is 12.5. And the units, if you're keeping track, are meters squared per second squared, because we canceled out kilograms. And then when you simplify all of that, 0.4 times 9.8 times cosine of 40 times 23.3 times -1, and you get a -69.97. There's more decimals. And you can finally say that's equal to 1/2 v squared. So it really has become much simpler. 147 plus 12.5 minus 69.97. And I agree, we're kind of running out of room here. That you still have positive energy, 89.53. We have to divide that by 1/2, so we have to really double that. Divide by 1/2 equals v squared. And I get a final v after square rooting everything of 13.4 meters per second. It's quite an accomplishment to get through any one of these problems. So nice work if you followed all of those steps, including friction on hills. They just take a while to set up. I'm going to continue to do the next one, but we won't talk through it. So feel free to scrub through, but I'm going to mute the audio.